I will share my screen. We go to the Bayes prediction, right? So how we use the Bayes theorem to predict the probability, as I said before. All right. So we review a little bit about the Bayes theorem or Bayes rule. Make it my slide is correct. All right, like this. Right. As we all know, the Bayes theorem says that to compute the probability, let's say event H, okay, with condition D, okay, where in here we have some notation. D is the data, let's say event data, just data like that. And then H is the hypothesis, okay, the hypothesis. So, according to Bayes' rule, the probability of event H with condition D, okay, is defined as the probability of event D, okay, with condition H, and then multiply with probability of event H divided by probability of event D. Okay, so this is by using the Bayes rule or Bayes theorem. Okay, so what are they actually? So in here we have some like notation, yeah. This is and this is the common notation that we know from the Bayes theorem. Okay, so PH is called the prior belief or probability of hypothesis H before seeing any data. Okay, so here is got the prior probability. Okay, the PH, this one, yeah. This one, okay, it's got the prior probability. Okay, how about this one? The PD slice H, okay, this one is got the likelihood probability, yeah. All right, whereas this one, the denominator or probability of this one also is got the priori probability. Probability. Okay, and the one that we look for is this. This one is called the posterior. Posterior probability. Okay, so this is a common notation from the Bayes theorem. Okay, so PH is the prior belief or prior probability, and then PDH a likelihood probability. All right, and you know the formula for PD/H, right? By using the conditions probability. We have discussed yesterday about this one, yeah. And then PD is the probability of the data, all right. And then this one is called the posterior probability. Okay, we have discussed this one. Okay, now we're gonna generalize the theorem because the events it's not only always one single event happens, right, or occur. Sometimes we have some features, right? So for that, we can generalize the Bayes rule actually. Okay, now we're gonna talk about that one. General Bayes theorem or generalized Bayes theorem. Okay, so before that, we agree first with notation. Okay, because there are many notations that we use, so we have to agree this one first. So T here stands for the target of an event. Okay, and then L is level or values, yeah. So you know every features has values or it's called the level. Okay, so it's in here with the notation is L. Okay, oh, okay, so L is the level or values of the target T, even if it's specific. Okay, so it means if I have probability of P of events t with values L. So this one is called this one, yeah. So this is the meaning of that. Okay, the level of target T, right? And then Q, let's say, is features. So Q consists of some features, yeah. So that's why is the is bold one. Bold in mathematics is called the vector. Vector consists of some columns, right? So like this. So this is Q is the feature. So sometimes, for instance, we have Q1, Q2, and so on. Okay, so this is the features. Right. Now with one target with a specific value and with some features, we try to predict what is the probability of target, the event of the target, okay, with condition Q1, Q2, and so on. Okay, so not only two events like we discussed before, what is the probability of event A with condition B? It's not like that, but now we extend the features. Okay, we we extend the yesterday we have definition evidence, so we extend that. Okay, so to make Bayesian prediction, we generate the probability of the event, which is the target T, with a specific level L, okay, given the assignment of values to a set of descriptive features K. So the features also has the value, okay. So some facts that we have here. First, T target with value L, and then features with some specific values as well. All right. So we're going to predict what is the probability of the targets. Yeah. So in this case, we can restate, restate from the original rule, from the original theorem. We're going to restate the Bayes theorem. Okay. In this case, we generalize the Bayes theorem. Okay. So that we can use it as the prediction. Okay, what is the form of the extended Bayes theorem? So in here, yeah. So this is the extended form of the Bayes theorem. So it's quite long because we have some features, right? The target's only one, right? That we're gonna predict, but the features is extended from Q1, Q2 until Qn. So this is the definition of the generalized Bayes theorem. So if we read this one, so it means the probability of target T, okay, with values L, with condition features Q1, Q2 until Qm. This one equals to probability of features Q1, Q2 until Qm with condition the target T equals to L, okay, multiply with probability of target T equals to L, and then divided by probability of features Q1 until Qm. Exactly the same as the original one, but the difference only the Q1, Q2 until Qm, right? So again, we have some notation here. So probability of T equals to L is called the prior probability. Okay. And then probability of Q1 until Qm is called the joint probability. Or is called the, this is apa? Prior, yeah. Prior probability. Okay. And then this one is called the condition probability, or is called the likelihood probability. Yeah, so they're the same. Okay, and then this one is called the posterior probability. Yeah. Okay. So we have extended form of the Bayes theorem. Okay, now how to calculate for each term of this? Okay, so this is actually explained to you how we compute for each term of the formula or the generalized Bayes theorem. Okay, first the probability of target t equals to L is simply the relative frequency which the target feature takes the level L in the dataset. So imagine you have dataset, okay, and then we have the target. Normally, the target lies on the right side on the table. Actually, normally it's like that, always on the in the corner of the table. Okay, that is the target. So you just need to find the frequency of whatever t equals to L happen. Okay, so like for instance, probability of t equals to yes. So you just need to find how many yes in this column. Okay, and then you have to divide by the whole of the data set. Right, that is how to compute the probability of t equals to L. Okay, next, how to compute probability of Q1, Q2 until Qm. That's similar. Okay, but now you just verify for each feature. Let's say you look at Q1. So how many I don't know, with for instance P Q1 equals to, let's say, blue, for instance. Depend on the problem, yeah, depend on data set. Let's say Q1 equals to blue, then you just look at the column Q1, then find the blue one, and then divide it by the total of n. Okay, so just see, and then for Q2 as well, for Q3, and so on. Okay, that's how to calculate that. All right. It can be also calculated by using the theorem of total probability. Yes. Ini kenapa dia merah nih? Probability. Alright. Okay, next. How to compute the PQ1 until Qm slash t equals to L. This is a condition, yeah. So probability of a feature Q1 until Qm with condition the t equals to L. So this one you can use the conditions probability. Okay, the one that we explained yesterday. So here can be calculated either directly from the dataset. So you have datasets, so you verify which one happens Q1, Q2 until Qm at the same time with t equals to L. Okay, and then you just divide by the total. Okay, or alternatively, you can use the chain rule. So this is explanation of the chain rule. Okay, chain rule. Do you remember chain rule in the differentiation? Huh? Similar with that. Yeah. So that's similar. Okay. So P probability of Q1 until Qm equals to. So this is by definition of the Bayes theorem. If you look at this one, yang ni. So you have equation 13, right? So if you want to compute the denominator, which is P probability of Q1 until Qm, this one. So how you do it? So this one actually equals to all of this one divided by the left one, right? So we use that one. Okay. So why this is not division? Because we change. So this one, for instance, we change with this. This one is slash, right? So this one until okay, until this. Oh, semua lah. Okay. So how you read this one? So probability of Q1 happen, right? Multiply with probability of Q2 slash Q1. Okay, slash Q1 means feature Q2 with condition Q1. Okay, and then multiply with blah 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 until Qm. So probability of Qm with condition Qm minus 1, Qm minus 2 until Q1. So that's definition of this. Okay. Now the equation 14 can be written as the 15. So this one, so probability of Q1 until Qm with condition t equals to L equals to P, okay, probability of Q1 with condition t equals to L multiply with probability of Q2, okay, slash Q1, okay, comma, t equals to L. So both of them. So the condition for the second feature with two condition, Q1 and T, right? And then the next one would be PQ3, the next one, yeah. If I continue this, times PQ3 with condition slash Q1 and Q2. So Q2, comma Q1 and T. Okay, and so on. Okay, so the last one, because the feature until M, then we have this one. Multiply with P QM slash QM minus 1 until Q1, comma T equals to L. Okay, so it means the probability of the feature M with condition other features plus the condition of T. Okay, so that's how to compute this. Okay, this one, yeah, the same. So this one now equals to all of this one, right? Or you can just go directly to the data set as I said before. Okay. Now we're gonna look at the example, okay? And how we implement this rule, okay, in the problem. Okay, so we look at again our data set, which is about the meningitis, headache, fever, and vomiting. Remember that? So where is it? Eh, dekat mana dia? Ni. Ya, this is our data set. Tak boleh besar kan? Okay. So we have 10 data set like this. Okay. This is our data set. What is the problem? Wait. The problem is we want to predict the meningitis actually. Okay. Okay, so now we're gonna calculate or evaluate the probability of people got meningitis with the condition or with the facts that they got headache, no fever, but they got vomiting. So by three conditions, the patient got the headache and vomiting, but no fever. Okay, then we're gonna predict whether the meningitis is yes or no. So the patient will get meningitis or no. So we're gonna predict that using the Bayes theorem. Okay, so let's do it. Okay, so because we want to predict this one, so if I convert this problem into the probability terms, so we're gonna have P probability of meningitis, right, with condition slash condition, okay, headache, H, right, it means H is true, okay, it says no fever, fever is false, then you can just write down like this, F, okay, in set theory it's called the neg, this term is called the negation, yeah, negation or something like this. It's mean none, yeah. Okay, and then vomiting, yes. So it's got V. we're gonna predict this. Yes or no? I mean, true or false? Yes or no? Patient will get meningitis or no with these three conditions. Okay, so therefore we just put this in the Bayes theorem. Okay, so the P of M slash H non F comma V equals to, by definition of Bayes, equals to P, the symmetry, yeah? If you remember the symmetry, this one and this one, you can see symmetry, right? So the posterior, the slash one is H non F and V, okay? But the likelihood, the opposite for this one. So now we have P of H non F comma V, right? And then slash M. So the slash now is M, okay? And then multiply with the probability of M. Then divided by probability of all of this one. H negative non F comma V. Okay, so this is from the Bayes theorem. Okay, now we're gonna evaluate one by one. Okay, so from the table, we're gonna look at what is the probability of this first. Okay, so in here, okay, let's, okay, ini sepatutnya M capital ya, just to be consistent. This one as well, M capital, M capital, M capital. Just to be consistent. Okay, now we're gonna look at one by one. Because in here, we have to compute PM, and then P this one, and then P this one. Okay, one by one, yeah? Okay, start from PM. PM means probability of meningitis, okay? So we look at our data set. Okay, this one, yeah? So we're gonna look at from this table. Tabelnya sekarang kat sini. Okay. So for meningitis, okay? So this one is called, this one is Q1, this is Q2, and this is Q3. Okay, nasib we just have 3 features, yeah? Imagine if we have 10 features, you have to compute for each feature. Okay, and this is the target, OT. And this is the false, this is the value. This is equal to L. Semuanya ni L. Okay? Okay, now we have to compute what is P of M. Okay, so you get just like yesterday, right? So we find the value of true 1, 2, and 3. Okay, so PM equals to 3 over 10. So this one, very easy. Okay, now the second one. Okay, now we have 3 conditions: H, non-F, and then V. So this one is false, yeah, non-F. So it's mean from this data set, okay, we look at 3 features. Which one that has values true, false, true at the same time? Because this one is joint probability. Remember, this one is joint probability. This is not condition. This is joint probability. Yeah, so you have to find for all of them. Okay, now we look at one by one. So true, true, false. This is not the one that we find, that we look for it. Okay, the second one, false, true, false, is not. Okay, this is not. And then the third one, true, false, true. Yes, this one, right? One. And then true, false, true. Yes, this is correct. Okay, the one that we look for it. Two. And then false, true, false. No. And then true, false, true. Yes. 3. True, false, true. Yes. 4. True, false, true. Yes. 5. False, true, false. No. True, false, true. Yes. How many? 6. 1, 2, 3, 4, 5, 6. So there are 6 with this value. So it means 6 over 10. Okay, so therefore here 6 over 10. Okay, settle for this one. Okay, which one again that we have to find it? So this one's okay. This one okay. Now for the condition 1. Always struggling with this, yeah? So it means with 3 probability of the 3 condition, no, probability of the 3 features with condition M. Okay, so from the data set, we look at first for condition M. Yang mana sahaja M? I mean M equals to true, of course, yeah, because M, not non-M. If it says non-M, means you find the false one. Now it's M, means you have to find the true one. So from this table, so we have 1, 2, 3 only, yeah? Kan? So that is the condition. Okay. Now, the features that we want actually Q1 true, Q2 false, Q3 true. So which one is it? So you can look at here. Okay. But with condition true, true, true. So you just look at the target first, true, and then you look at the left one, which one is Q1's true, Q2 false, and then Q3 true. This one's, no, it's not, because Q1 is false. Okay, now next, the second target, this is yes, yes, because true, false, true. So this is the one that we want. Okay, and then the last one, the target is true, the features satisfied, true, false, true, yes. So we just only have 2, but not 2 over 10, because 2, the total is 2 for the left one, but condition is 3. Okay, so we have the total is 2 over 3. Total. Mana dia? This one. Sekejap dia kenapa tak sampai sini? Terlalu besar. Dia macam hang sikit. Okay, this one ya. Tampak kan ya? Sekejap saya angkat. Okay, so now sampai mana tadi saya? Okay, explain this one. Okay, so this one ya. So we got this one already. Okay, now the second one. Okay, to compute this, so this one ya. So we have the rule. Yang ni belum lagi compute yang apa? Yang ni, probability of meningitis with 3 features. Yang ni belum lagi. We just finish for this one, settle, this one settle. Now we gonna find what is this. P, 3 features with condition M. Okay? Yang tadi itulah saya explain. So, probability of 3 condition, 3 features with meningitis equals to, according to this one, mana dia? According to, not this one. Nah, this one. According to this, okay, so we're gonna use that. So this one equals to probability of condition H with meningitis M, okay, multiply with the second one. This is the first one with M, and then the second one, non-F, okay, slash H, M. Remember that? And then the last one, because we have 3 features, P of the last one, V, okay, slash with sama je, H, non-F, and then M. Clear? So this is from equation. Tadi saya kasih nama berapa? Number 15. Okay, from equation 15. This one, yeah, from equation 15. From equation 15. Okay, so if you have 5, the same thing. So the first feature with the condition, and then multiply with the second feature slash feature 1 with condition m. Okay, and then multiply with what is it, the second feature slash the first feature, this and then the m, the target. Okay, and then multiply with the third feature. Okay, slash the first feature, the second feature, and target. Always like that, and so on. Okay, so that is the chain rule from the equation 15. Okay, and that's to compute if you have probability, if you want to find the probability of some features with condition the target. This is the way how to compute it, right? Okay, we done for this one. Clear yang clear ya, this one ya. So this one h slash m. Okay, now this one, the second one. So probability of non f, okay, slash h comma m. So we look at from the table. Now condition h and m means a headache and meningitis. Where is the table? Okay, headache and meningitis. So you just look at the target because the target only has 3 true, right? Now you look at the headache, the true one. So for this one, the headache is false. No, we don't choose that. And then the second one, the meningitis true, and then the headache true. Yes, we choose this one. And then the last one, true, true for the headache. So we choose the only 2. Okay, so it means 2 divided by 2 because condition only 2. Okay, so now we have 2 over 2. All right, so with the same thing as this, the last one. So probability of V, condition vomiting, not condition, probability of feature V, okay, with condition non F, H dengan M. Okay, now look at here. Meningitis only 3. Okay, tadi apa? Non non F. Okay, non F. Sekarang you tengok target dia true. Okay, and then find non F, not fever. Yang mana yang not fever? This one true. The fever is true. We don't choose that one. And then this one, yes, we take this. But you look at first the vomiting or not. V, yes, true. So we choose this one. Okay, and the last one true with this is true. And then the fever is false. Yes, we choose this one. And then the vomiting true. So we choose 2. So the same thing as previous probability is 2 over 2. Okay. Okay, and then you multiply all of them, and then you got this one. Okay. Okay. Alright, we continue again here. So now, once we compute all of them, so we got this one, PM, and then P, the 3 features, H non-F, B, and then the conditions, probability, H non-F, B, with condition M. Okay, then now we compute what is the probability of people got meningitis with 3 conditions, uh, uh, two conditions with headache and vomiting, but non fever. Okay, so here we go. So now we're using the Bayes theorem. This one, yeah? Bayes theorem. Okay, so we substitute everything that we have. So this one equals to 0.666, right? And then PM 0.3, just multiply with this. And then the P of this equals to 0.6. Okay, and then use calculator or you can use manually, it's okay. Then finally we have this one. So the probability of people got meningitis with symptoms headache and vomiting and not fever is the 0.333, which is quite small actually, right? Not really big probably the chance. Okay, only small. Okay, on the other hand, because this is probability of people got meningitis, we can also find the people who didn't get the meningitis. Okay, just the opposite for that. Okay, because remember, if we have uh, 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 event A, okay, and then we have the opposite of this is non-A, right? So if P of A equals to 0.3, for instance, then P of non-A equals to 1 subtract with 3, 0.3, which is 0.7. So just only vice versa. So we do the same thing in here because this is for meningitis with H non-F V. Okay, so we can also compute on the other hand. Okay, so P of negative M, not negative, yeah, non-M, not meningitis, but with the same condition. Okay, so the result is this. So if you compute this one, add with this equals to 1. Okay, without using the chain rule, you can just go what is actually the probability of non-meningitis. Okay, just only 1 subtract with 0.333, which is 0.6667. Right? So actually it's quite rare because not rare, it's quite weird because many I don't know the symptoms of meningitis, but without fever, is it possible if a patient got didn't get fever and then what is it? It just got headache and vomiting. Then the conclusion, the prediction, he didn't get meningitis, right? Because the meningitis only 0.33, which is quite small. Compare with the meningitis 0.67. So it means the chance of the patient got meningitis only 0.333, which is very small compared to non-meningitis. Right. So this is yang ni lagi besar daripada yang ni kan. So it means if the patient got headache and vomiting and without fever, means the patient didn't get meningitis. That's the conclusion for that. Right. Okay. So very nice of Bayesian, right? We can predict like that. Okay. That's from the 3 features. We can play around these features. Okay. At the moment we just have features headache, and then non-F, and then V. You can explore more. What if the patient only non-headache? He got fever, he got vomiting. What is the chance? What is the probability of people got meningitis with this condition? Also, another one, if people, the patient got headache, got fever, got vomiting. We don't know yet. You can compute that by following the same rule, the same formula. Okay? Or not all of them. Ada tak di sini semuanya false? False. Oh, tak ada. Oh, unfortunately, we don't. Oh, we have data for false, all of them. False. Oh, there is no. Always false, true. Okay. So if you want to take the condition non H, non F, non P, there is no data for that because everything like this, true to false, right? There is no false, all of them. Kan? Yeah. So you can play around with this. So try this one and try this one. Okay. On non V, for instance, you got headache F and then non V, for instance. You can play role with this. Okay. Then you will see, you will evaluate what is the chance for patient got meningitis. Okay. Okay, this is the one that I already concluded, right? So the chance of patient got meningitis with two symptoms, okay, is quite small, okay, compared with non-meningitis. Okay. Okay. Right. And this is actually leads to another definition from the Bayes theorem. Okay, we'll see here. So calculating exact probabilities for each of the possible target level is often very useful to a human decision maker. For example, a doctor, of course, yeah. Because not only guessing, but we can calculate exactly, okay, by having the data set, and then we can compute, we can predict in exact values how much what is the probability of patient got certain disease, right? And very useful to the doctor. However, if we are trying to build a predictive model that automatically assigns a target level to a query instance, then we need to decide how the model will make a prediction based on the computed probabilities. Okay. The obvious way to do this, to have the model return the target level that has the highest posterior probability given the state of descriptive features in the query. Okay, so you want actually to get higher the posterity. Posterity in the is the probability of the target. Yeah, and how to do it? How to make higher posterior probability is by computing the maximum posteriori, or is called the MAP. This one, yeah? Maximum of posteriori. So we want to maximize the target value, the probability of the target, right? So we have another definition. It's called the MAP, maximum of posteriori. You know posteriori on the left side, this one, yeah? Yang ni. Ini yang ni disebut dengan posterior. I already mentioned before, right? Okay. So we want to make this one maximum. Okay. Therefore, we use definition maximum of posterior. Okay, here we go. So actually, in the Bayes theorem, we have two condition, two hypotheses. Okay. First is called the maximum likelihood. So we can maximize the likelihood. You know, this one is the likelihood. Yang ni ya. This one is the likelihood. Okay. Or we maximize the posterior, which is the left one. Okay. If we want to maximize the likelihood, this is the formula. So HML, maximum likelihood, equals to maximum of probability of D slash H. Alright. Whereas if you want to maximize the posterior, this is the formula. All right. So here H means the hypothesis or the features. Yeah. Same. Okay. Okay. Let's have one example just to make it clear. Okay. Consider this actually the same story with before. Yeah. Consider a medical diagnosis problem in which there are two alternative hypotheses. The patient has particular form of cancer, and the second one, the patient doesn't have the form of cancer. Okay, the positive and negative. Positive mean got cancer, negative didn't get cancer. So we have prior knowledge that over entire population of people, only 0.008 have this disease. Okay, so with in the one population, okay, we have prior knowledge means from experience in the past. Okay, only the chance people got the cancer only 0.008. This one. Okay, so it means P. This one P, yeah? P of people got cancer positive. Okay, equals to 0.008. Right? And then another fact, the lab test is only an imperfect indicator of the disease. Okay, so the test returns a correct positive result is only 98%, not 99, yeah, of the cases which the disease is actually present. So it means if the disease presents, the disease exists, and then the patient got the test, the positive result is only 98%. Okay, and the correct negative, this is positive, yeah. The correct negative only 97% of the cases. Okay, okay. So if patient got cancer and then he got test, okay, the positive result is 98%. Okay, but if the patient didn't get any disease, the negative cancer, all right, and then he got the test, so the correct negative result is 97%. Okay, so this is the illustration. So now we're gonna solve this one. So the problem is now, what is the probability of the patient got cancer, right? So again, this one, what's the patient got cancer? Okay, we look at here. Okay, from these facts, okay, from all of these facts, we try to uh, what is it? Classify one by one which one has value. Okay, the same thing if if you are given problem, for instance, I don't know, in the exam or in the assignments, any facts here you have to write down. So for instance, like this. So from the prior knowledge, the probability is 0.08. Okay, just write down this one. Okay, now we write everything here. Okay, now probability you got cancer 0.008 according to the fact, according to the problem. Okay, and then according to it means, okay, if we got P cancer 0.08, it means P non-cancer is 0.992. How you got this one? Is 1 subtract with 0.008. Yeah, so you got this one. Okay, now the probability of the test is positive with condition cancer. It says 0.98, right? According to this story. It says, mana tadi? Nih ya. Okay. So the patient who got cancer positive, sorry, the patient who got the cancer and then he got the test, okay, and the correct positive is 98%. So we can write down like this. So the condition now is cancer. So the slash is cancer, okay, and then the probability is the positive. So this is 0.98 the value. Okay, and from this one also, so we can also write down this one. So 1 minus 0.98. Okay, how to read this one? So it's mean the probability of negative with condition cancer is 0.0, very small actually. Okay. Okay. On the other hand, if the patient got cancer, the patient didn't get cancer, and then he got test, okay, the probability of the chance the test is negative is 0.97 according to this story. Yeah, right, right. What is it? Yeah, this one. According to this story, 0.97. So that's why we have this one. Okay, negative non-cancer. Okay, and the same thing. So if you want to find what is the probability of positive slash non-cancer is 0.03. Okay, that's the same thing. One subtract with 0.03. Okay, okay now. So based on these facts, you want to predict new patient. So the patient coming to you, let's say just imagine you are a doctor, okay? And then we have all of this value, all of this fact. So probability of cancer as this, all of this one. Okay? Okay, now a new patient coming to you. You want to diagnose, you want to predict whether the patient got cancer or not. Okay? So of course you want to see the test first. Okay, so the test is positive or not. Okay, okay, so therefore we use the equation 14. Okay, so here we go. So okay, now for this one, without looking at one or two particular features, in this case you have to compute all of the possibility of features, all of them. So that's why we in here we use the map maximum posterior. So we have to compute all of the features. Okay. So in this case, just only two is okay lah. But later on, we'll have another example which consists of many features. So you have to compute all of the possibility in the features. Okay. Okay. So now let's do it. So first, you have to compute the probability of positive on the test. Okay, with condition cancer, right? And then multiply with probability of the cancer. Okay, so this value is 0.007. All right, and then the second one, so probability of non the negative, yeah, so the negative test with non-cancer, and then multiply with probability of non-cancer is 0.02998. Okay, so based on this we have to find the maximum, right? So because this one is greater than this, so 0.0298 is greater than 0.0078. So it means you can be confident says, so the probability of the patient didn't get cancer is greater than that. So it means the patient didn't get cancer because it says here. So H map equals to non-cancer because this one is greater than this. Okay, but if finally you got the cancer one is greater, then the conclusion is H map equals to cancer. Okay, maybe you will ask me how to compute this one. Well, you look at again the equation 15 ya, 14, 15 and Bayes theorem. Okay, nah yang ni please refer to equation 14, 15. Yeah, I already explained before, right? Then you got this one. All right. Okay. Cek lagi. Okay. Um. So this is illustration how we maximize the posterior. Okay. Now under the Bayes theorems, okay, we also has another definition. It's called the I don't know how to spell this one. Brute force Bayesian, BFB. Okay. So what is it? So you can look at here. So this is actually the relationship between the Bayes theorem and concept learning. Concept learning means like machine learning. Yeah. What is actually the relationship between them? Okay. So therefore we have this definition, brute force Bayesian. Okay. So what is it? So the brute force map, okay, of learning algorithm have two steps. Okay, first, for each hypothesis H in domain H, calculates the posterior probability. So as I said before, if you have some features and target, let's say, so this is Q1, in this case H, yeah, okay, let's say H1, H2, H3, okay, and then let's say target. Okay, so according to this algorithm, you have to compute all of the target value. So let's say your T1, T2 until Tm. Let's say T10. Okay, so you have to compute P, T1 slash all of this one. H, yeah. D, what is D? Uh, 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 uh. Data, yeah. D is data, right? Yeah, data. Ini berapa? Lepas tu P, T2 slash D berapa? And then find the maximum one. So the maximum one is the prediction, your prediction. Actually, it's simple as that, actually, by using the Bayes. There is actually a relationship between Bayes theorem with the machine learning or the learning algorithm. Okay. So this is the way. Okay, so first you compute all of the hypotheses. Okay, and then the second one, the output of the hypothesis is the highest posterior probability. Okay, the highest posterior probability. That is the your prediction. Okay, so if you have only 10 features, it's okay. You can do it manual. Okay, but imagine if you have more than that, 100 features. Okay, let's say 10 features is okay, but the data, 100. Can you do it manually? So therefore, you're gonna learn in this night actually with Danang, okay, how to compute, how to implement the Bayes theorem to predict uh, any problems. Okay, you can implement this one. Once you got the code, you can change the data by this one, and then you'll see, you'll be interested for this one. Okay, as I said, if the data only 10 data, like in this example, it's okay, you can just do it manually. Okay, so but you have to compute all of them. Okay, but if the data is more than that, I don't think you can do it manually. So you need the uh, programming for that, right? Okay, so this is the MAP algorithm. Lima lagi Pak. Saya takut terlanjak. Okay. Sorry. Okay. So to implement the brute force learning algorithm, the following assumptions are applied. So first, the training data D is noise free. So what's the meaning of the noise free is this ya. Misalnya ada apa arrow macam ni. So this is definition. Okay, the data is assumed noise free. It means probability of data slash H hypothesis equals to 1. So the probability is really correct. Okay, and uh, this the value this equals to 1 if d di equals to hxi. Okay, and then otherwise the probability equals to 0. That is noise free. So it means there is no outliers in this case. Yeah. And then the second one, the target concept C is contained in H. And then we consider a prior all the hypotheses equally probable. Okay. So this one. Right. So this is the assumption. Okay. So if H is inconsistent with D, then the value of PHD equals to 0. Alright. But if H is consistent with D, then the value equals to 1 multiplied with all of this one. Okay. So this is only just only information. Yeah. We not really use this one. Okay. Okay. I'm gonna continue first, and then later on, if you have questions, you can ask me. Yeah. Okay. So this is the last section. Still, we use the Bayes theorem, but now we focus on the classification. How we use the Bayes theorem to do the classification. All right. So the algorithm or the model is called the Bayes naive. Naive, yeah. I don't know. Naive means like, uh, what is it? Lie or something not trusty. Actually, naive, right? But we use it because it's quite nice prediction actually. We will see. Okay. Okay. So before the naive Bayesian, we have a definition first: conditional independence and factorization. Okay. So conditional independence. So as I mentioned before, if you have two events X and Y and they are independent, okay, it means probability of X doesn't affect the probability of Y. That is independent. Okay, and we have forms, special form for the two independent events, which is this one. So probability of X slash Y equals to Px if X and Y are independent. Okay, or Px comma Y, okay, equals to Px times Py. So this is the mutual, yeah, joint probability. If they're independent, this one is happen. Okay, but if it doesn't independence, then we have another condition. Okay, but in reality, it's very rare to get some features are independence, really independence. Okay, uh, very often happens if, let's say, we have three conditions. Okay, x, y, z. Okay, let's say x and y are independent. Okay, but they are independent if z uh, actually occurred. But if z didn't occur, that didn't happen, then a and b are not independent. So that's a very common happens in the reality. Okay, with if the features really independent is quite rare in the reality. Okay, and this is the happens, right? Okay, now for two events X and Y, they are conditionally independent given knowledge of the third event. So let's say Z, then we can say that's this. So this is if we have three events, yeah, with two of them are conditions. Okay, so probability of X slice Y comma Z equals to actually probability of X slice Z. So they are the same. Okay, and then the second one, probability of x comma y slash z equals to this one. Okay, and again, the chain rule, recall, if we use, this is only three features, right? If we want to extend them, then we'll have the formula 17. This one only three, but now we have many features. Then this is actually the formula. Okay, so P Q1 slash target, like this. Okay. Okay. Now actually, this is still the same thing as the previous formula. Okay. Now with conditions Q1, Q2, and so on are independent. Okay. Then the equation 17 can be simplified as this. Okay, so in here there is no more Q3 and so on. Let's say in here in Q1 there is no more Q2, right? Because they are independent. Okay, whereas in here, if you can see here, so we have, let's say, to compute the Q2, so you still need Q1. To compute Q3, still needs Q2 and Q1 and so on, right? But now since the conditions, we assume they are independent, then we have this one, equation 18. So if you can see, there is no more in Q2, for instance, there is no more Q1. In Q3, let's say we have Q3, there is no more Q2, and the same thing as this. In the QM, we don't have QM minus 1, for instance. So it means they are independent. Right. So very simple formula now we have. Okay. This simplification is important since it allows us to simplify the Bayes theorem under the assumption of conditional independence. So this one also effect to the Bayes theorem, because previously Bayes theorems is used to where the events are not not independent. But now, since we have assumption of the independence condition, of course we're gonna have the simple Bayes theorem. Okay, which is this. So this one's before independent. This one is not independent. So the features are not independent or dependent lah. Not independent. This one, the features are independent. Okay, so very simple now, right? Compare with this. Okay. Okay, that's definition of conditional independence, probability of that. Now we look at what is the naive Bayes model. Okay, so a naive Bayes model returns a map prediction, okay, where the posterior probabilities for the levels of the target feature are computed under the assumption of the conditional independence. So that's why we need this definition, conditional independence, because the naive Bayes model only is implemented where when the condition of the features are independent each other, right? So that's the condition of the knife. Yeah, this actually cannot be used in the general form. Yeah, just only for the certain condition, which is independence condition. Okay, and more formally, the naive Bayes model has the formula as equation in 20. Okay, this one. So this symbol means multiply, ya. You have to familiar with this, ya. Nah, yang ni, this one is multiply. Okay. Okay. So here we have maximum. Maximum comes from the MAP. Yeah, we use the posterior maximum. Okay, and this is the multiplication between each features with condition target. Okay, and lastly, we multiply with probability of target equals to L. Okay, yeah, then becomes simple. Okay, okay. So there are some advantages of the naive Bayes model, as you can see here. Yeah. So first, for instance, uh, okay. So the naive Bayes model is naive because the assumption of conditional independence. Yeah, because we can't use it for the general form. Yeah. So what if the features are dependent each other? Then we can't use the naive Bayes. Okay. Between the picture and the okay. Despite this simplifying assumption, however, the naive-Bayes approach has been found to be surprisingly accurate across a large range of domains. So that's why people still explore about the naive-Bayes because this accurate prediction that we have so far. Yeah. And then this is another advantage. Okay, you can just read it. Okay. And now in the in the machine learning, the Bayes theorems or naive Bayes model is used to optimize the result of the prediction. Okay. Okay, let's have a look at the example how to use the naive Bayes model. Okay. Okay. Oh, gambar siapa nih? Okay. So this is let's say we have data set. Okay. How many? One, two, three, four, five, six, seven. Oh, very easy. Eight only. Yeah. And also the feature only name and then the gender or sex. All right. And your task is you predict if someone's coming to you, the new person coming to you, you have to predict is a woman, a male or female, like that, without looking at the hair, for instance, just only by the name and then the gender or the sex only. Okay, so we're gonna predict if in this case an officer, yeah, an officer is male or female, like that. Okay, so you predict. Okay, this is the data set. So if the name is Drew, it's male. Claudia, female. Drew again, female. Drew, female, and so on. So how many we have? Drew, Sri, Nina. Okay, just it, yeah. Okay, now how to predict that? We use the Bayes theorem. Okay, and particularly we have to compute all of the features and then find the maximum one. Okay, so this is the formula that we use. Okay, J means many, yeah, many data, yeah. Start from 1, 2, and so on. Okay, first, for instance, we compute probability of male, okay, with condition Drew. So from here, we have to find, so by condition, yang ni, use this one, yeah, okay, so male and Drew, okay, so the total is 1 over 3 times 3 over s is divided by 3 over s equals to 0.125. Okay, that's for male because we want to predict male or female. So you have to compute both of them. Okay, male with the name of Drew. Okay, I think I have another one again. Oh, tak. Okay, salah satu je. So male with the name of Drew And then because we want to predict this one, the name of Drew, officer with name is Drew, male or female? Okay, male or female. And you can also play around with this. You can predict officer with Claudia name. Okay, we are not sure it's female or male. Okay. Okay, so this is the probability 0.125 as for the Drew is male. Okay, now if Drew, the female with the name of Drew with condition is Drew. Okay, so if you compute this one, blah blah blah, using this Bayes theorem, so the value is 0.25. So which one is bigger? This one. Okay, so this one actually is bigger than ini salah lah. Ya. Yang atas nih less than this. Right. So 0.125 is less than 0.25. So it means you can say, you can conclude that Drew is a female. Okay. Is it female or male? Here we go. Correct classification. Okay, so first you just cover the face. We don't know the face is actually female or male. And also just like playing game like this ya. And also the hair, we don't know what the hair. Yang dekat sini pun tak ada hair dia kan. So dia cover the hair, but we have to predict if the name is Drew actually is female or male. Because the data is Drew is male. Kan ada 2 yang female tapi ada 1 juga yang male. But you have to make prediction. Okay, so this is the officer Drew. Alright.
Doctor,
Okay. Yep.
how they calculate the probability? 1/3 times with 3/8, right? And then divide by 3/8.
By using this one.
But I don't get 0.125.
You mean when you multiply this one, you don't get this one?
Yes.
Really? Coba 1/3 darab dengan 3/8. Ini cancel kan? Dapatlah 1/8.
Yes.
And then you divide it by 3/8. Kan?
Yes.
Ataupun menjadi 1/8, 8/3. 1/3. Oh yeah. It's wrong. Thank you. Yeah, this one not 3/8, but 1/3, right?
Yes.
1/3, which is 0.33.
333.
Kalau yang dekat bawah?
Bawah. Female,
Betul.
which means 2/3, right? Not 1/3.
Coba Tak, maksudnya value dia dah betul 0.25.
But
Tak.
saya confused yang untuk female punya dia supposedly 1/3 or 2/3. But female for Drew.
Two. Yeah, because two females.
Yes.
One. Siapa salah? Dua lah. Okay, ini 2. 2/3 multiply with condition Drew. Drew ada berapa? 3 kan? 3.
Yes.
And then multiply with condition of
Female.
female. 1, 2, 3, 4, 5. 5 ya?
Yes,
Ini
5/8.
pun dia hanya 3/8. Itu 2, 3, 4, 5 lah. Okay, you baikilah. Oh, maybe the classification is not female. You boleh kira lah. Maybe this is wrong. Yeah. Alright. Okay, thank you, Siti Hajar. Okay, this is just like illustration. about the naive Bayes classification. Okay, and we have another data sets. Now we extend. We add some features. Yang tadi hanya name and sex, right? Now we have over 170 centimeter. We have eye. Oh, sekejap ya. Okay, so we add some features now. We have the height over 170 center or not. So this the data is no, yes, like this. And then the eye. So the officers got blue or brown like that, only two. And then the hair length, short or long. So now we have some features. So how to compute them? Please use a similar way. Okay, use the chain rule. Okay, but you have to think. This is actually independent or in unindependent. Sorry, dependent or independent features. Independent, right? So from name, for instance, there is no. If you have name Drew, there is no connection with the heights, right? There is no connection with eye. There is no connection with hair. It's not necessarily if you have short hair and then you got blue eyes. There is no connection, right? So for all of them, I think they are independent. If they are independent, then you use the formula of independence formula from the bias. Okay, this is actually illustration for that. From the data, you can also use write on the table to make it clear. Okay, so like this. So based on the sex, for instance, this one not 190 but 170. Macam mana ni? Okay, and then sex with long hair. Okay, and then and satu lagi apa dia? And I. So you can have some not classification, because we want to find we want to evaluate all of them, right? All of the male and female based on the features. For every features you have to compute them and then find the largest one. That's the prediction. So you have to compute like this. So for instance, here's sex with um, uh, so here male, but you have to do it, yeah. Male. Kenapa tak boleh? Allah, hang lagi. Tipu je semua macam ni. Okay, never mind. Tak perlu conteng-conteng lah. Okay, it's like this. So, first, male with height. Male or female with height. You have to compute all of them. And you got this one. I don't know whether they are correct or not. Okay, and then male with long hair. Female with long hair. Okay, and then the next one, male with eye. Female with eye. Then from that you compute the using the Bayes theorem, and then find you have to compute all of this one, PD1, PD2, and so on. Okay, and then find the largest one. Okay, and another example for the naive Bayes theorem, you can refer to this book. Okay, page 323, section this one, which is this one. Okay, work example. In here we have a data set regarding the transaction, right? Transaction is fraud, true or false, like that. Okay, you can read this one, and there are some what is it, solutions as well, but it's already here like this, but you can compute it by yourself, right? So look at here. So for each condition we compute, like this one, ch non, and fraud, cs paid, fraud, for all of them, because here we have some values for this one, right? For instance, for credit history, ch here, credit history. For the currents, so what is the probability if this condition with the fraud true, and then again another condition with fraud false, for instance. So you have to compute all of them. So like this. Okay. After that, then you're gonna short it. Which one is the largest one, right? Okay. See, like this. So because the last one we got this one, which one is greater? 0.0245 means the probability of the transition is not is not is true, not true, yeah. Non, it means false, right? The transition is false with the conditions. How many conditions? The chance is 0.0245. Okay, this means the transition is true, right? Is true. Is false. Sorry, because none, yeah, none is greater than this. Is false. Something like that. Okay. So not only one condition you compute, but all of them, all of the feature you have to compute, and then you compare, right? Okay, to make it more clear, you can also do this one. Okay, so you are given data sets. What is it? Age, income, student or not, and then credit rating. Okay, and then people will buy bike or not. So this is the one that we want to predict. Okay, we want to predict people will buy a bike or not, by which condition. So it means you have to compute probability of yes with all of the condition: age, income, student, credit rating. Okay,